Okay, once again, we've got three more work questions, and we'll have a look at them one by one. In the first case, you've got somebody lifting a 50-kilogram box to a height of 1.5 meters. And we want to know, is the work converted into kinetic or potential? Well, first of all, we're lifting the box vertically. We're giving the box an additional height, so we know that the work we're doing is being converted into potential energy. So we can focus on that equation to solve this. Now just remember, change in anything in physics is always final potential energy minus initial potential energy. And we've got an easy formula for potential energy. It's just mgh. So this would be mgh final minus mgh initial. Now we're starting at the ground, so my initial height was 0 and my final height was 1.5. So when I do this, I simply go 50 kilograms times 9.8 meters per second squared times my final height, which is 1.5 meters. And when I crank all that out, I get 735 joules of work done. So the work I do provides 735 joules of potential energy to the box. The other way to do it, we can imagine work as force times distance. And in order to lift a box, the box has a force of gravity down. The only way I'm going to get that box to move up is if I apply an equal and opposite force in the upward direction. So I've got to apply a force at least equivalent to the force of gravity. So the force will be force of gravity. The distance is still 1.5 meters, but you'll notice it gives you the same result. Force of gravity is mg times 1.5 meters, which looks exactly like this. Next question. A rock of mass 4.7 kilograms is lifted from a height of 2.1 meters to a final height of 3 meters. How much work is done on the rock? Now again, we're lifting it, so we're giving it potential energy. We're gaining height with that. Now, I don't have a picture of a rock, but this serves a purpose. So we can see we've got this little line here lifted high. Initially, we can imagine it was down in this position here. And it starts at a height of 2.1 meters. And it ends up at a height of 3.0 meters. And in order to lift that rock, we've already established that we have to apply a force equivalent to the force of gravity to get it to move. So we're going to focus on our work as change in energy formula. And we're giving it potential energy. So this is potential final minus potential initial. And in this case, we actually have both terms. So this is mgh final minus mgh initial, which is, if I factor out an mg brackets h final minus h initial. Now the mass was 4.7 kilograms. Gravity was 9.8. H final was 3 meters. And H initial was 2.1 meters. And I'm sure we can work that out. So that'll give us joules of potential energy. Now when I calculate it, I get 9.8 times 4.7 times my change in height, which was 0.9 meters. I get 41.4 joules of energy. Now, once again, I could just do force times distance, where my force is the force of gravity, equivalent to the force of gravity, except I'm acting in an upward distance or an upward direction to actually overcome the force of gravity. The distance over which that force acts would be 0.9. So it would just be mg times 0.9 meters. And again, that's the same as what we did down here. Very last question, very, very similar. We're taking a golf ball and we're lifting it out of the hole. So once again, we'll use change in potential energy because that's what we're giving it. We're not giving it kinetic, which is mg, we'll cut to the chase here, h final minus h initial. The mass is in grams. It must be in kilograms. So a 46 gram ball is 0.046 kilograms times 9.8. H final was 0.95. And H initial was on the ground, so it's 0. So all we need is the final height. And when I push all that through my calculator, I get 0.046 times 9.8 times 0.95. And I get 0.43 joules of potential energy is what's given to that ball. So the work done was 0.43 joules, which goes into giving that ball potential energy.